Hello, my name is Luis Serrano, and this video is done with Zapata computing, and it is about quantum machine learning, in particular, quantum generative machine learning. But do not worry, you don't need to know any of those words before. You don't need to know quantum computing, and you don't need to know machine learning in order to understand it. Obviously, it helps if you do, but everything we need, we're going to introduce it as we go. Now, why quantum computing? Well, because quantum computing is here to stay, and the rise has been monumental. Quantum computing is quickly finding applications in most fields out there, and machine learning, being a field that has applications in pretty much everywhere, is no stranger to that. In fact, most applications of machine learning are actually finding their place in quantum computing now, and vice versa. So sometimes quantum computing helps machine learning, and sometimes machine learning helps quantum computing. So in this video, you're going to learn a very useful connection between quantum computing and machine learning. Are you ready? Let's begin. This video is actually part of a series of a lot of information. The first one is a blog post on the advances of quantum generative machine learning written with Zapata computing. The video itself is split into three. This video has the fundamentals of quantum machine learning. Then video 2 is about non-gradient optimizers used to train these machine learning models. Now, video 1 is not going to be very heavy on the math. It's going to be very heavy conceptually, but there's not going to be a lot of formulas. The formulas are all in video 3, the math behind qubits. And all the links to the blog posts and these videos are in the comments. Now, as I mentioned before, for this video, you don't need to know what machine learning is or what quantum computing is. Of course, it helps if you know either one, but it's not required. But long story short, in machine learning, there are these objects called neural networks which process information from left to right, and we tune them in to produce exactly what we need them to. In quantum machine learning, we got these circuits on the right that resemble neural networks, and just like in classical machine learning, we can tune them in so they can produce exactly what we need them to. Of course, the rules of the game are slightly different, but the concepts are pretty much the same. So here's a big picture of machine learning. There are two big areas in machine learning called supervised and unsupervised machine learning. Of course, there are many more, like reinforcement learning, etc. But for now, we'll focus on these two. Because as we've observed, some things are easier for classical computers and others are easier for a quantum computer, and here seems to lie an important division. More specifically, in some subfields called discriminative learning and generative learning. What is discriminative learning? Well, this one consists on answering questions like yes or no. For example, an image recognition model whose job is to recognize faces will take an image and return a yes or a no depending if the image even is a face or not. Generative learning is a huge and very trendy area of unsupervised machine learning, which consists of creating new data. An example of generative model is a model which can draw human faces at random. Recently, with the development of generative adversarial networks and other similar models, the kind of images neural networks can draw are quite impressive and very difficult to tell apart from real images. And of course, any sensible course on machine learning will start with supervised learning and then much later move to generative learning, and this is a much harder topic. For computers as for humans, it is much harder to draw an image of a face as it is to be able to recognize that an image is a face. However, in our approach to quantum machine learning, we'll do the exact opposite. We'll start by learning quantum generative learning. And why is this? Well, both classical and quantum computers can run both discriminative and generative models, and I'd like to emphasize that great work is done on both types of computers for both types of models. However, we have noticed that there are certain aspects of classical computers which make supervised models more natural on them, and similarly, aspects of a quantum computer which make generative models more natural on them. Allow me to elaborate. One reason for this is that classical computers are great at performing calculations, namely operations with a well-defined input and output. This is the essence of supervised learning, as supervised learning always has an input and an output. Quantum computers have a particular strength, and is that they can generate truly random numbers, which is something that's hard for classical computers. And they need no input for this, only output. And that looks a lot like what a generative learning model does. Of course, in both cases, we have to really tune in the parameters of the models to get them to output what they want. But let's focus our attention on generative learning. There are a plethora of generative machine learning models, both in classical and quantum machine learning. To name a few, in classical machine learning, we have generative adversarial networks, restricted Boltzmann machines, variational autoencoders, among others. And in quantum machine learning, we have quantum generative adversarial networks and quantum Boltzmann machines, and quantum circuit-borne machines. It is this last one, the one that I'll introduce in this video, the quantum circuit board machines, or QCBM. So my favorite way of looking at quantum computing is using probability. Well, that's actually also my favorite way of looking at machine learning. And my favorite way of looking at most things in life is using probability. So that's what we're going to use to connect quantum computing with machine learning. And what is the simplest example of probability? The first one that comes to mind is a coin flip. So imagine you have a coin, and this coin may be fair or it may be biased. That means the probability of falling heads may be 50%, but it could also be any other number. And when you flip the coin 10 times, you get 6 heads and 4 tails. That is our data. Now here's the question. If I were to tell you that there are 2 candidates for the coin that generated these coin flips, which one of the following would you pick? We have coin 1, which from now on we'll call model 1. This one falls in heads with a 60% probability, or 0.6, and in tails with a 40% probability, or 0.4. And then we have coin 2, or model 2, which falls in heads 10% of the time and tails 90% of the time. So they're both biased. Now, if you had to emulate the results on the left, the data, which of the models would you pick? Which of the 2 coins would you pick? And if you're like me, you'll most likely pick coin 1, or model 1. And it's much more likely that if you throw this coin 10 times, it'll fall 6 times in heads and 4 times in tails. It could be coin 2, there's no guarantee that it isn't, but coin 1 is just much more likely to be our coin. And indeed, if we pick coin 1 and we flip it some more, that gives us some generated data. And the generated data is likely to be 6 heads or 4 tails. It could be anything else, but it's likely to be that, or at least close to that. And this is actually a general form of a generative machine learning model. We have some data, which would be coin flips, images, text, or anything. And then this data is fed into a model, which in our previous example was the coin. This model learns the data, and by that we mean it tries to understand patterns on it and tries to learn from which probability distribution it could have come from. In our previous example, this is when we figured out that the most likely possible coin that generated those flips was the one in which the probability of falling in heads was 0.6. And finally, when the model learns the data, it is able to generate some new data, which is what happened when we flip the coin some new times, and obtains data that looks a lot like our original data. And that is the point of the model, to create data that looks as close as possible to our original data. And this data could be pretty complicated. For example, generative adversarial networks can take images of human faces and produce some very realistic looking images. But let's get back to our example with simple data, which is coin flips. This is a simple generative model, and one that can be very easily modeled on a quantum computer. And that's what I'll show you next. So now that you know what the simple generative model looks like, the next question is, how do we model that in a quantum computer? Well, it turns out that this one is actually one of the simplest quantum computing exercises out there. It's pretty much the 101, the hello world of quantum computing. And for that, we require the building block of quantum computers, the qubit. In order to learn what a qubit is, first let's look at its classical counterpart, the bit. When I think of a bit, I always like to think of a light switch with 2 states, on and off. And for the purpose of this video, we'll have on as a red 0 and also an up arrow, and off as a blue 1, which is also a down arrow. You may be used to seeing on as 1 and off as 0, but this is how we'll see it here because it matches the quantum computing lingo more. Now, a bit can be in any of those 2 states, 0 and 1, and that's it. And a classical computer is an ensemble of lots and lots and lots of these switches or bits that are in some state, and they get manipulated in the ways that we need in order to store data and solve any problem that we want. Now, its counterpart in a quantum computer is called a qubit, which is short for quantum bit. And I like to see those not as a switch, but as a slider. A quantum bit also has the on state, also represented by a red 0 or a red up arrow, and an off state, again represented by a blue 1 or a blue down arrow. Sometimes the arrow is called spin, so we refer to the qubit as having spin up or spin down. Notice that the 0 and the 1 in the qubit are between these strange walls, one straight and one bended. This is called the Ket notation, which is standard for qubits. But here's the interesting part of qubits, and is that they not only can be on states 0 or 1, but they can also be in any superposition of the states 0 and 1, just like you can turn a slider into light on, light off, or somewhere in between. For example, they can be on half 0, half 1, like this one, or you can have, let's say, 3/4 0 and 1/4 1, or 1/4 0 and 3/4 1, or pretty much any combination that you can imagine. So instead of thinking of a switch that can be on or off, let's think of a slider that can be in any position between 0 and 1. Now, qubits are a little more complicated than just a dimmer. In the previous dimmer, the half-half superposition of 0 and 1 could only be one state, but in a qubit, each superposition can actually appear infinitely many times, except for the pure 0 and 1 states. A qubit can actually be seen as a whole sphere. This sphere is called the Bloch sphere. In the Bloch sphere, there's a north pole, which is the state 0, the south pole, which is the state 1, and all the points in between correspond to superpositions of the states 0 and 1. Now, how much of 0 and how much of 1 is in the superposition is given by the height of the point. For example, all the points in the equator at the very middle are a perfect 50-50 superposition of 0 and 1, although they are all different states. Now, notice something interesting. The classical bit has two states. However, there are infinitely many states in a qubit. Does that mean that they can carry a lot more information than one bit? Will one qubit be enough for us to tell between infinitely many different things? That would mean that qubits can carry pretty much an infinite amount of information. But that's not true. Qubits do carry a lot of information, but there is a catch. When we look at these qubits, the state collapses into only one or two choices, as I'll show you next. So let's say there's a qubit in some superposition of states 0 and 1, and we decide to look at it to see in what state it is, or in what superposition. Well, what happens is that when we look at it, two things may occur. One is that the qubit goes all the way to the north pole to state 0, and the other one that it goes all the way to the south pole to state 1. And once this happens, we have no way of knowing what state the qubit was before we observed it. All that information is lost. And here's something interesting. The probability of the qubit going to state 0, 1 depends on where it is right now. More specifically, the closer the qubit is to the north pole, the most likely it is to go there, and similarly with the south pole. So for example, a qubit that's on the equator will have a 50-50 probability of going to the north pole or to the south pole. This process is known as quantum measurement or observation. Now, the way I like to look at it is by imagining a huge red magnet in the north pole and a huge blue magnet on the south pole. They both pull the qubit, and the higher the qubit is, the more likely it'll be caught by the red magnet. So for example, this one was up, so it's a 0.7 probability of being caught by the red magnet and 0.3 of being caught by the blue magnet. However, if the qubit is already in the north pole, the probability that it gets caught by the red magnet is 1. And similarly, if it's in the south pole, the probability is 1 that it gets caught by the blue magnet. Those are the only states where we're certain. For everything else, there is always some uncertainty. Now, here's a connection to machine learning, in particular to generative machine learning. Each qubit can be a generative or a probabilistic model. In the lingo of the earlier example, a qubit can model a biased coin flip. If we want, say, a coin that lands in heads 60% of the time and in tails 40% of the time, we simply prepare this state over here. And if we want another one that, say, lands with heads 10% of the time and with tails 90% of the time, then we use this qubit over here. Now here's a question you may be pondering with. What is this superposition mumbo jumbo? What do we mean that a qubit is in a superposition of two states? If I don't know what the state of a qubit is, that doesn't mean it's a superposition. That doesn't mean that when I look at it, it makes up its mind. It could be that it's there already, like a coin, right? If I flip a coin and it falls, for example, in heads, the coin is in heads. And if I don't know what it is, it's still in heads. The universe knows, right? It's a bit arrogant to think that if I don't know what it is, then it's not defined, or the universe doesn't know either. The universe knows, and the coin knows. They're just waiting for me to find out. When I observe, I'm a passive observer who just happens to find out if the coin is heads or tails. Well,
It turns out that with qubits, that's not the case. Quantum physics, things behave very, very strangely. And it turns out that, to the best of our knowledge, what happens is that the qubit is in a superposition, and that when we look at it, we change it, and it becomes a certain state. And if we were to assume that the qubit is determined, and that when we look at it, we're passively not changing it, then we're going to reach the most bizarre contradictions. So let me show you one of these contradictions.
So for this, let's consider the following thought experiment. You have a box, and inside this box you have a glove that could be red or could be blue, but it could also be a right hand or a left hand. And we don't know the color or the shape. So far, as far as we know, it could be any of the four scenarios, but we're going to assume that it's deterministic. Now, we'd like to know what color and what shape it is, so we can do two observations. The first one we can make is we can open a little hole in the box and look at it. And let's say we look at it and find out that it's red. So this is a way to find out the color, and the color only, because we don't know the shape. So we have a red glove. And this observation is consistent. If I were to do it many times in a row, I keep getting red. So we're pretty sure it's red. Another observation we can make is we can close our eyes and stick in our hand in the box and look at the shape. So let's say we found out that the shape is a right hand. And again, this observation is consistent. If I do this many times in a row, I keep getting right hand. However, there's a caveat, which is that I can only do one of these observations at a time. I cannot do both at the same time. I can't open the hole, look at the color, and at the same time stick in my hand. It has to be one or the other. But up till now, we're pretty sure that we have a red right-handed glove. However, let's check. Let's verify that we have indeed a red glove. Let's look at the color again. And we open the little hole, we find out that what? It's blue? Why is it blue? It was red. What happened? What did we do wrong? Well, it turns out that what we did wrong was assuming that things were deterministic and that observing didn't change things. It turns out that we are forced to assume that the glove can be in a superposition of shape and color, and that when we look at it or we touch it, we actually change it. This is how qubits operate. And I'll show you next how this works. So when I told you we can measure qubits, I left an important detail out. We can measure qubits corresponding to a basis, and the basis can be many things. And when I say a basis, I really mean a pair of antipodal points. So for example, the standard basis is the basis corresponding to the north and south pole. If I measure with respect to this basis, then the qubit will either go to the north pole or to the south pole. However, for a basis, I can also pick any pair of antipodal points. For example, these two over here. And when I measure with respect to this basis, then the qubit can go to any of the two antipodal points. And what are the probabilities? Well, you guessed, the closer the qubit is to each of the antipodal points, the more likely it is to go there. So for example, the qubit on the right is more likely to go to the green point than to the yellow one, but it could go to either one, right? And here's an interesting thing. Measuring on different bases tells us different properties of the qubit. So in our thought example, imagine that the 0-1 basis measures the color of the glove, is red or blue. So north pole means red and south pole means blue. And this other basis, which is called the plus-minus basis over here, measures the shape of the glove. So if it's on the right, the glove's a right hand, and if it's on the left, the glove's a left hand. And this is out of scope of this video, but in a qubit, you can measure many properties of it. For example, the spin, the momentum, the energy, etc. But you cannot measure them at the same time because these measurements require using different bases. So you may have heard that in a particle, you cannot see its velocity or momentum and its position at the same time. And the reason for that is precisely this, that to find out the momentum and to find out the position, you need to measure using different bases. And you cannot do them at the same time. And the results of observing in one basis could change the other one. Let me show you how. So we're going to perform the exact same experiment with the glove, but now we're going to perform it in this qubit. And it's all going to make sense. So in the beginning, say the qubit is in this state over here, which is a superposition of red and blue, and also a superposition of right and left. So we're in a superposition in terms of everything, color and shape. Now we want to check the glove's color. So what do? We measure with respect to the 0-1 basis, which is a color basis. And when we measure, then the qubit decides its color. It decides that it's going to be red, and it's still in a superposition with respect to the shape. Now let's say we want to find out the shape. So for this, we want to measure with respect to the shape basis, the plus minus basis. And when we do that, notice that this qubit is in perfect superposition of right hand and left hand. Because with respect to the yellow and the green points, this point is in the equator. Basically, if you tilt your head 90 degrees, then you have the North Pole, the South Pole, and the equator, and the points in the equator. So it could go to either one. Let's say it goes to the green one with 50% probability. So now we have a right-handed glove, but the glove doesn't know anymore if it's red or blue, because now it's not on the North Pole or in the South Pole. Now it's in the equator with respect to the 0-1 basis. So we go back to measure the color, then the glove doesn't have color anymore. It's now in a perfect superposition. So it could go red or it could go blue. And let's say we're so unlucky that it went blue. So we had a glove that first was red and now it's blue. And what happened is that very observation in the middle of red and blue, when we looked at the shape of the glove, when we measured using the plus minus basis, it changed the qubit and it removed the certainty on the color. Now that's strange, isn't it? And that's how quantum physics operates. It's very strange, very bizarre, and this is just one of the many, many, many experiments that we can make that will completely blow our minds when studying quantum physics. Now, there are three most important bases for measurement, and there's a standard 0-1 basis called the Z basis. There's a standard plus-minus basis, which is the one we just saw, called the X basis. And then there's another one, which is the Y basis, called the plus I and minus I. And these come from complex numbers because actually the complex numbers appear a lot in quantum computing. So, however, for the purpose of this video and all the algorithms we're going to learn here for generative machine learning, all we really need is a standard 0-1 basis. And measurement this basis will be associated with this logo over here, which represents a measuring needle. So whenever you see this in a circuit, it's because we're measuring that qubit.
So now that you've learned that any qubit in any state can be thought of as some coin flip, or more technically, like a very simple machine learning generative model, here's a small caveat. Building or preparing qubits in any state is not a walk in the park. Once we figure out what state we need our qubit to be in, we actually need to devise some methods to get a qubit into that state. And for that, we use quantum gates. The concept of gates is very similar to that in classical computers. Let's recall that classical computers have bits, which can be in state 0 and 1, and in order to flip and operate with these bits, there are gates, such as the AND, the OR, and NOT, XOR gates, etc. Well, quantum computers are not that different. You've seen that they have qubits instead of bits, and just like classical computers, they also have some gates that operate on these qubits. There are many gates, but here we learn some that are pretty fundamental. These are the rotation gates and the entangling gates. Let's start with rotation gates. A rotation gate does exactly what you imagine, which is rotate the qubit. An easy state to have a qubit is the state 0. So let's say we have such a qubit, and now we want to get to the state over here. What we do is we use a rotation gate, or perhaps a combination of rotation gates, that will rotate the sphere in the right way to get to that qubit. There are three fundamental rotation gates, each one corresponding to the three fundamental axes of rotation, X, Y, and Z. And in any of these axes, we can rotate an angle of theta. These gates correspond to the rotations called Rx of theta, Ry of theta, and Rz of theta. And here's our very first quantum circuit. These are represented by wires in which the qubit goes from left to right, passing through gates, etc. So here, for example, the qubit is on the left at the 0 state. It goes through a rotation gate Ry that rotates it an angle of pi over 2 radians, putting in a perfect 50-50 superposition of the states 0 and 1. And then the qubit gets measured using the standard 0-1 basis, and as you've seen already, there's a 50-50 chance that it goes up and down. This is like flipping a coin. So let's say it goes down, which means a tails gets recorded. If we run this experiment many times, then roughly we'll get heads 50% of the time and tails 50% of the time. Therefore, this circuit perfectly models the tossing of a fair coin. Now, what if the coin is biased? Well, we can do the same thing except rotate a qubit at a different angle. Let's say we rotate it just the right amount to make the toss a 60-40 toss for heads and tails. So we can run this experiment many times and get heads 60% of the time and tails 40% of the time. So now you've learned that quantum computing can model the tossing of any coin no matter how biased. Now what if the experiment gets more complicated? Well, let's go for the next level of complexity. 2 coins. So now let's say I have 2 coins, the circle coin and the square coin. And I flip this coin many times, and 25% time I got heads heads, 25% I got heads tails, 25% tails heads, and 25% tails tails. So just like before, let's say that there are 2 possible pairs of coins, or 2 possible models that could have done this. The first one, which we're going to call model 1, is a pair of fair coins. That is, coins that return heads with 50% probability and tails with 50% probability. The second model is a pair of biased coins in which the first coin lands in heads with 90% probability and the second one lands in heads with 80% probability. Now, of course, both models could generate this data. Potentially, they could give us these results, but which one is more likely? Well, I'm sure you'll agree with me that in order to get the same probabilities, it's much better to use model 1 and the 2 fair coins. So we'll use that one. And the reason is that the throws are independent and the probability for heads heads and heads tails, etc. are the product of the individual probabilities, which is 50 times 50 equals 25% as expected. These products of independent probabilities are easier to see when we look at areas in a square. So on one side we have the first coin, which gives heads and tails 50% of the time, and the other side we have the second coin, which gives the same proportions. And the probabilities for the combinations of heads, 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 tails, etc. are the areas of these squares that are formed, which are all 25%, or 1/4 of the area of the big square. Now, how do we model this in a quantum circuit? Easy. We do the same thing as before, except now we use 2 qubits completely independent from each other. Each one of them gets rotated to exactly be on the equator, and then they get measured. When they get measured, they can return 0, 1 with equal probability of 50%, and the measures are independent of each other. So we record the 0 as tails and the heads as 1. This circuit perfectly models the 2 independent fair coin tosses, and this can be verified by repeating the experiment many times and noting that the histogram formed by the results shows the 4 options heads heads, heads tails, tails heads, and tails tails roughly an equal number of times each. Now here's a slightly harder problem. We've tossed 4 coins and notice that the results are the following. 72% of the time we obtain heads heads, 18% of the time heads tails, 8% of the time tails heads, and finally 2% of the time tails tails. And now the question is, among the following 2 models, which one is more likely to generate these results? Model 1 is a model with 2 fair coins, and model 2 is a model with 2 coins, the first one generating heads with 90% probability, and the second one generating heads with 80% probability. So which one do you think is more likely? And I'll write these numbers here to help us out with the decision. And if you're like me, you may have picked model 2. Because model 2 has a higher probability of heads for both of the coins, and the data has a much higher probability of heads for both of the coins. So that's the hint. And this actually works perfectly. The numbers here work exactly as they should. And to verify this, we can see that if we make the same square as before, where the first coin corresponds to the left edge and the second coin to the top edge, the probabilities are 90-10 and 80-20, and the probabilities for both of the throws are the products of these, or the areas of the squares. So for heads, heads is 90% times 80%, which is 72%, and for the others are something similar, 18%, 8%, and 2%. And again, this can also be modeled with a very simple quantum circuit. Not very different from the previous one. In here, we need to rotate the qubits the right amount of radians. So in the first RY, we rotate a very small amount, and the second one just a little. And the probabilities of measuring the qubit as 0, or as equivalently the coin falling on heads, is 90% for the first one and 80% for the second one. Now, running this experiment many times will result in roughly the following histogram, which is very similar to the original data. Now, here's an even harder problem. Imagine that I tossed two coins 100 times, and now I'm telling you that I got the following results. Half of the time I got heads heads, the other half of the time I got tails tails. And that's all I got. I never got head tails or tails heads. What do you think of these results? Is it possible that two independent coins that I could have tossed, no matter how biased, would give me these results? Well, as you're imagining, this is a bit bizarre. So you may be imagining that perhaps I cheated. Or perhaps that I used some strange coins. Because if you were to pick a coin, no matter how biased, that gives probability of heads and tails, and another coin that also gives probabilities for heads and tails, there will be some probabilities in all these boxes here. It's impossible to get 50% of the area on heads heads and 50% of the area on tails tails and nothing on the other two. So perhaps my coins are in some way connected. These measurements are not independent anymore. Now they're correlated. So the question is, are the coins talking to each other? Perhaps I devised a pair of coins that when the first one falls on tails, it sends a signal to the second one and says, hey, I'm heads, so the other one does the same thing. And when the first one falls on tails, then it tells the other one, and the other one does the exact same thing. So the second coin is designed to fall in the same way as the first coin. They're not independent. And one would say that the coins are entangled. And that's precisely the phenomenon that makes this happen on quantum circuits. So quantum entanglement is one of the most fascinating and entertaining. And entangle is precisely where we're looking here, because this is an actual phenomenon called quantum entanglement, which is one of the strangest and most fascinating phenomena in quantum physics. So imagine that you have two qubits in some state, and in some way you join them or entangle them in a way that when we measure them now, their measurements are correlated. So for example, they could both end up in the same state up or in the same state down. Now this entanglement can be strange. Imagine this. There are two entangled qubits, and you and I take one each. Then we go to different galaxies many light years away. When you measure your qubit, then my qubit instantly changes. Say if your returns a state 0, then so will mine. Einstein always found this very puzzling, as it seemed to imply that the qubits are passing information to each other at a speed faster than light, which is impossible as nothing can travel faster than light, including information. Thus, he referred to it as spooky action at a distance. For many years, scientists tried to understand entanglement, including trying really hard to explain it as a classical phenomenon. For example, the following question arose. What if the qubits are not talking to each other or communicating or connected in the same way? What if before getting separated, they simply talk for a long time and come up with a very detailed plan that says exactly how they'll behave if they're measured on any basis? This plan could have thousands of pages, but the important thing is that each qubit takes the plan with itself when they get separated by a long distance. Then each qubit performs the plan as accorded when they get measured. This theory got debunked by several experiments that show that indeed it is impossible for the qubits to know exactly what to do with separate plans. The plan has to be conjoined. They have to be correlated in some way. And in some way, what happens in one qubit affects the other one, even if there is a very large distance in between. Now, we're not going to get into the entanglement math in this video in detail, but just know that there are different levels of entanglement. That's all we need to know for these machine learning purposes. For example, the case in which the qubits were independent had zero entanglement because the two coins land independently. The extreme case, where the coins return only heads heads or tails tails, is the most entangled state. This is called the Bell state. And in between, we have different levels of entanglement that can vary. There's a particular gate called the Monmouth-Sorensen gate, which can entangle our qubits, and it works just like a rotation gate with an angle input. And if the angle is 0, then we have a pair of qubits on the state that is completely unentangled. So if we give it a pair of qubits on the zero state, it does nothing to them. And as this angle gets bigger and bigger, the correlation between the two qubits gets higher and higher, all the way to the Bell state, which is the highest entanglement state. The Molmer-Sørensen gates are labeled XX, YY, and ZZ. Although for the purpose of this video, we'll only need one. Say the YY gate. So in short, if we want a circuit that entangles two qubits, we can use a Molmer-Sørensen YY gate, which given the correct angle, in this case the highest angle, we fully entangle the qubits. And when we measure, then we either get heads or tails. So we'll roughly get the histogram on the right, in which half of the time the two qubits are 0 and half of the time they're 1. In other words, we're modeling a pair of entangled coins which always falls in both heads or tails. So the story goes like this. After the quantum computing professionals learned how to rotate a qubit and to entangle a qubit, they just went out in the wilderness and started building all kinds of states, right? Well, ideally, but it turns out that these states are hard to build. Imagine if you have a lot of qubits and you want a particular entangled state, and all you have is rotation and entangling gates for two qubits. Well, it's going to be hard to figure out how to put them together to get the entangled state. So I'm going to show you how to do that next. So here's a harder problem. Let's say that we have now 4 coins. And these coins are quite special because when I toss them, I always get either 4 of them heads or 4 of them tails. I never get anything else. So out of the 16 possibilities, I only get the first and the last. So these coins are quite entangled. And now, we would like to model this as a quantum circuit. How do we do this? Well, given what we have is not going to be easy. We only have rotation gates that take care of 1 qubit and entangling gates that can only entangle 2 qubits. How do we fully entangle 4 qubits? That's going to be hard. And we can get creative. We can say, well, perhaps we have a circuit with some rotation gates here and some entangling gates here, each one of them with a completely different angle. That won't be easy. So let's take a standard approach. What we're going to do is we're going to pick some fixed architecture, so some fixed gates locked in position, and we're only going to worry about finding the angles. If you think about it, this is very much how machine learning works, how regular neural network works. We pick a fixed architecture and then we find the parameters that best solve our problem. And here is one of the architectures that we'll use. This one works very well in practice. As input, it has all the qubits in the 0 state. Then it has a layer of RY rotation gates. Then a layer of RZ rotation gates. And finally a layer of YY Molmer-Sørensen gates that connect the first qubit with all the other ones. And of course at the end we measure all the qubits. This is one of the 3 types of architecture that we'll study today. These are also called topologies. First is the star topology, the one we just saw, in which the YY gates connect the first qubit to all the other ones. Then there's the line topology, in which one connects each qubit to the next one. And finally, the all topology, the most complete one, which is the one that connects each pair of qubits. And just like with regular neural networks, we can add layers upon layers. For example, here's an example of a circuit with 3 layers using the star topology. Here's the first layer, then the second layer, and finally the third layer. This type of circuit is called a QCBM, and it has been discovered by Benedetti, Garcia Pintos, Perdomo, Leighton Ortega, Nam, and Perdomo Ortiz. To see more information, please check out the link in the description of the video. And now the goal is to find a set of angles for which when we measure the circuit many times, we get the histogram on the right, which is roughly the state 0, 0, 0 half the time and the state 1, 1, 1, 1 the other half. If those angles don't exist, then at least we can get the angles that get the closest. So this process is called training the model, and we'll see more of it next. Now, in order to train a QCBM, we'll actually change the dataset a little bit. It's not going to be the dataset of 0000 and 1111. It's going to be a slightly more complicated one, but the process is exactly the same one. And the reason we're going to use this dataset called bars and stripes is because that's a toy dataset that we use a lot in generative models. So here it is. The bars and stripes dataset is this one in terms of coins. When we flip the 4 coins, we only get these 6 states, each one with a 1/6 probability, and we never get any of the other states. Why is it called bars and stripes? Well, because it simply consists of images inside a given rectangle which correspond to coloring any set of vertical bars or horizontal stripes. For example, here's the bars and stripes data set for a 3x3 square. Notice that coloring all the boxes corresponds to all the stripes or all the bars, and coloring no boxes correspond to no stripes or no bars, so those also belong to the dataset. And how do we encode a particular element of the bars and stripes dataset? Well, we simply code it as a bit string, where one color becomes 0 and the other color becomes 1. And it doesn't matter which one we choose, as at the end we get the same strings. So for example, here are the 16 ways to color the boxes in a 2x2 square. And also the 16 possible bit strings of length 4. And the ones that correspond to bars and stripes are precisely these 6 over here. And that is why this is the bars and stripes dataset. And this is a toy dataset that we use a lot to test our generative models. So we're going to use it to test the QCBMs. So the bars and stripes distribution looks like this. And this is basically a histogram in which each of the bars and stripes appears 1/6 of the time and all the other ones appear 0 times. So in other words, it's this probability distribution. And that's the one that we're going to model using a QCBM. So we're going to try to figure out a circuit that will generate this precise histogram. So remember when I mentioned before that quantum machine learning is a lot like classical machine learning? Well, in particular, as you can see, the QCBMs look like the circuit on the right, which kind of resembles a neural network. So in classical machine learning, we fix an architecture and try to find the parameters that will make the neural network output something as close as possible to the labels in the dataset. In quantum machine learning, we fix a quantum circuit architecture and try to find the parameters, in this case the angles of rotation and entanglement, that will get the circuit to output something as close as possible to the distribution we're looking for. And as I mentioned before, QCBMs can have the star topology, the line topology, and the all topology. So we're going to pick a star topology for this one, but actually there is a lab that I'm linking in the comments, and that one will have the all topology. And so say we select the star topology with a layer of y rotations, a layer of z rotations, and then a layer of entangling yy gates. And what happens is that the 4 qubits get rotated in the y direction, then they get rotated in the z direction, and then the first 2 get entangled in some way, then the first and third get entangled in some way, then the first and fourth get entangled in some way. So now we have a really entangled 4 qubits. Then they get measured, and let's say that we got up, down, down, up. So that's heads, tails, tails, heads. So we're going to say that this circuit took the qubits in state 0, 0, 0, 0 and turned them into the state 0, 1, 1, 0. Now, we could run this circuit again and get something completely different because there is this measuring step that is random. So the idea is to try to get the circuit to output the right histogram that we want. So here's the idea for the training. Imagine that we start with some random angles, say theta 1 to theta 11. And when you measure this many times, you'll get a histogram, say like the one underneath. So here's the idea for the training, and by training I mean finding the right angles that will do the job. Imagine that we start with some random angles, say theta 1 to theta 11. When we measure this many times, you get a histogram, say like the one underneath, where each bit string has some probability given by the height of the bar. However, we don't want this histogram. We want something like the one on the right, in which the bars and stripes appear with probabilities 1/6 and all the other ones with probabilities 0. So somewhere in the universe there must be some 11 angles, say phi 1 all the way to phi 11, that will do the job. Or perhaps some angles that will get close enough, or somewhat close. Who knows? There's got to be some best set of angles, and we want to try to learn those. So when we get these best angles, that's what we call training the model. And that's what I'll show you next. But before we get to the training, it's an important question, which happens in classical machine learning too. What architecture should we use? Should we use a star topology? Should we use an alt topology? Should we use 1 layer, 2 layers, 3 and 10 layers? So just like with neural networks, it depends on the problem, on the data, and on many things. But the rule of thumb is to try to use the simplest architecture that works. Obviously, the more layers, the more entanglement gates, the more likely is that the QCBM will work, because the more complex the model is, the more likely there will exist some set of angles that work. But at the same time, the more complicated the architecture, the harder it is to train or to find these angles. So it's not easy to decide, and the best thing to do is to try several models and see which one is the simplest one that does the job decently. So now the question is, how do we find the correct angles in our circuit? This is the process of training, and it's very similar to the one in classical machine learning, using optimization methods. So here it is. The process is called DDQCL, or Data-Driven Quantum Circuit Learning, and it works like this in a nutshell. Let's say we have our circuit over here, and when we sample hundreds and thousands of times, we get this distribution over here. But as we saw before, that's not the one we want. The one we want is this one, which has the bars and stripes data set. So just like in machine learning, we're going to do an iterative process consisting of the following 2 steps. First, we compare the histogram we have with the histogram we want, just to see how far we are from our goal. Then we use this comparison to update the angles in our QCBM circuit. So we open the hood and fix it inside. And if we do this many times, always getting a slightly better circuit, you can imagine that one day we'll hopefully reach our goal, at least get something pretty close, just like in classical machine learning. Now you may be wondering, how do you compare the distributions and how do you update the angles? So there are many ways to do this. To compare the angles, there are several methods, including KL divergence, log likelihood, or maximum mean discrepancy. I'll tell you what KL divergence is in a bit. To update the angles, we can use derivatives, a common method such as gradient descent, but we can also use non-gradient methods that don't use derivatives, such as covariance, matrix adaptation evolution strategy, or CMAES, and particle swarm optimization, or PSO. So let me start by showing you KL divergence. So Kullback-Leibler, or KL divergence for short, is a very effective way to compare 2 distributions. What KL divergence does is that it returns a small value if the distributions are similar and a large one if they're different. For example, these 2 over here look quite similar, so the KL divergence has got to be small. But for these 2, they look quite different, so the KL divergence should be large. And the formula is simply this. You may see it as a very similar formula to entropy. And it's actually the difference between the cross entropy and the entropy. So it's always non-negative. And when we have the same distribution, Px and Qx, then this is 0, because we have a bunch of logarithms of 1. And when these 2 are very different, this is a large positive number. And so now that you know how to compare, what's missing is how to update the angles. So this part is long, so we've actually separated into a different video where we explain CMAES and PSO. Actually, non-gradient methods are more common than gradient methods for these type of circuits, because a gradient method depends on a derivative. Sometimes these circuits are hard to find a derivative. Sometimes you can, but sometimes they're very challenging. And so that's why we normally resort to non-gradient methods. So I recommend you the other video, the link is in the comments. But other than that, this is the training process, and I hope you find it similar to the machine learning training process, where it's an iterative process that gets better and better and finally gets some pretty good angles. Now, when you train this in different architectures, these are the angles that were obtained. And in the links, and also in a little bit, I will tell you about some labs and some workflows that you can run in order to find these angles, and that you can play with to find, for example, angles for other different data sets, etc. Well, I hope you enjoyed that, and if you did, I'd like to invite you to check out this lab where QCBMs have been coded in a very simple way, and it's also very flexible. You can change the data set, change the error function, etc. You can see that it did quite well with bars and stripes. You can also check out Orchestra, which is the platform that we have at Zapata for running quantum workflows. There is a QCBM demo in Orchestra, which you can check in this link, which is also in the comments. And that demo comes with a video where we show you how to do, again, the bars and stripes distribution using Orchestra. And if you're interested in finding out more about quantum machine learning or quantum computing, check out zapatacomputing.com or orchestra.io/docs, or tweet at us at Zapata Computing. So thank you very much. I would also like to recommend you my book called Grokking Machine Learning, and this is my YouTube channel. Make sure you subscribe or hit like if you'd like to see more material like this, or add any comments. I really enjoy looking at comments. Or you can tweet at me as well. Luis Likes Math is my Twitter handle, and my page where all this information can be found is serrano.academy. So actually, if you're interested in the book, here is a discount code for 40% that you can get by buying it on that webpage. So thank you very much for your attention, and see you in the next video.